Proficiency in math among U.S. pre-college students is overall stunningly low, as shown by reliable long-standing empirical data collected annually. This is especially true, and distressingly so, for students in lower socioeconomic levels. In New York urban school districts, only 13% of 3rd through 8th grade students were proficient in math, and in fact, 68% of these students scored at level 1 on their math test, this being a level that no test taker, however scant their progress, can fail to achieve. In stark contrast, in districts where residential real estate is very expensive, and correspondingly, the vast majority of K-12 students hail from households of a high socioeconomic level, math proficiency is markedly higher. For example, in 2019, overall, 88% of students in Scarsdale School District were proficient in math. Such inequity is profoundly disturbing. After all, it is difficult to see how youth from lower socioeconomic levels will have a decent chance to avoid poverty in an economy that is increasingly driven by mathematics, computation, and specifically by the development of, in collaboration with, artificial intelligence and machine learning. To solve this problem, we propose bringing to bear a distinctive class of artificial agents that can augment conventional math education of U.S. students. To begin with, let's address the math test in question and what content is to be taught. New York State's K-12 public education system conforms to a set of expectations set out in natural language known as the Common Core Standards. These standards are all capturable in computational formal logic. Specifically, Common Core standards are captured by a set of formulae expressed as such, in the formal language, expressed as such, of some formal logic, again expressed as such. The subscript in here refers to grade level, so this particular example expresses the Common Core standards for grade 3, captured. And the collection of all Common Core standards, which the to-be-explained master method has as a static resource, is denoted as such. Now, the specific math test and the standards that they are based on, with which we are concerned with, are, with minor variation, ubiquitous across public K-12 education in the United States. But we key in on these tests as they are developed, administered, and statistically analyzed in New York State. As a first example, consider this grade 3 question here. An interesting note is that there is more than one way to solve this problem. Specifically, there are 2 different pairs of rectangles that one can use/imagine in order to select the answer. Accordingly, the system will find 2 different minimal proofs automatically that establish that the answer is indeed 22. A harder, more interesting problem is this grade 4 math question shown here, where what the student provides as a justification is understood to be a proof, or at least an argument, for the selected option, and is assessed by our AI technology as such. While such tests, as created and provided by the New York State Education Department, do not include requests to test takers that they provide justifications, though some questions do request that work be shown, in our approach to AI-infused math education in the early grades, we believe it's important that the students attempt to provide justifications that are precursors to the proofs that will eventually be requested of them in high school, and if not there, then certainly in college-level mathematics.
To ground our discussion of our Type A class of artificial agents, we'll start by reviewing some very general AI concepts and move to the more specific components of Type A agents. So first, what is AI, and specifically what is logicist AI? So we affirm the uncontroversial orthodox conception that the discipline of AI consists in the attempt to understand, design, and implement artificial agents. Okay, so now what is an artificial agent? Again, this definition has been affirmed by the major AI textbooks by Russell and Norvig and another by Luger. That is, an artificial agent is an entity which receives percepts from its environment and outputs actions which are performed in its environment. So now more specifically, what is logicist AI? It is the same pursuit of the overarching field of AI, except the function which receives percepts and generates actions must utilize automated reasoning. So a little later, we'll get into more of the specifics of how we utilize automated reasoning in this way, and some reasons why it's desirable. Before that, I'll briefly mention psychometric AI. So this is very simply the endeavor to create AI agents whose cognitive abilities can be concretely measured via some tests. This approach to AI is directly applicable in the present work, as the type of agents we propose to address the math gap problem need to be able to solve standard math problems and assist students in learning how to solve those problems. Next, we discuss the 6 key elements of our brand of Logicsys AI as they pertain to the creation of TIP-A agents. So I'll go through them each one by one. The first is cognitive calculi. And while a full discussion of exactly what cognitive calculi are is out of scope, they're essentially quantified multi-operator modal logics, in which the proof theory is specified in natural deduction form, and there are modal operators for human level cognition, such as believing, knowing, perceiving, etc. And the semantics are entirely proof theoretic in nature, and so this is opposed to model theoretic or possible world semantics. So in this work, we utilize a specific cognitive calculus called the deontic cognitive event calculus. Again, I think it's out of scope to show the entire syntax and semantics of the calculus, so I'll show you one inference schema to give you an idea of how it works. So this is schema 11a, and so this basically says that if some agent A believes at time t some formula phi, and also believes that phi implies psi, then the agent can infer a belief in psi. So essentially, this schema is capturing the idea that agents can deploy modus ponens on the contents of their beliefs. So the second element is automated reasoning for cognitive calculi. Several automated reasoners are actively in development for various cognitive calculi. The one we employ in this work is called Shadow Prover, and soundness proofs have been obtained in prior work, but of course are out of scope here. The third element are visual logics and associated automated reasoning. So as it's likely clear at this point, TIP-A agents need to be able to reason not only over purely symbolic content, but pictorial content as well. So for this, we'll employ the Vivid framework for pictorial reasoning. Fourth is background axiom systems for mathematics itself. So the idea here is that we want TIP-A agents to be able to generate their own test questions using automated reasoning and background axiom systems for the relevant area of mathematics being tested. So in our current case of interest, grade 3 and 4 mathematics, a simple axiom system for arithmetic called Robinson arithmetic is sufficient. Fifth, we must capture what is specifically to be learned in an axiom system. So this is because Common Core standards are written informally in natural languages such as English. So these standards must be captured into formal logic in order for TIP-A agents to reason about them. Finally, TIP-A agents require natural language processing of our Logicsys sort in order to communicate with students. So this includes both language generation as well as understanding, which is done via constrained form of English, which can be captured in the formal grammar. And again, as with all of our other components of our work where semantics are involved, our natural language semantics are also entirely proof theoretic in nature, as opposed to model theoretic or Montesquieuian semantics.
TIP-A, as a paradigm, is a class of artificial intelligences that are enabled by cognitive logics to offer a continuous assistive experience through multiple heterogeneous hardware environments for the users whose education they are enhancing. They are designed to accomplish this task by fulfilling the properties of their namesake, TIP-A, teleportative, intelligent, personalized, persistent agents for education. These properties, formalized and verified through the use of logic-based artificial intelligence, aim to create agents that are not only helpful to their users' education, but open avenues for the potential of human-computer friendship. In brief, the properties of this paradigm can be described as thus. Teleportative represents the need of the agent to be able to teleport, also known as migrate, through many potential hardware environments while giving a believable impression of being one uninterrupted AI identity. Consider, as a hypothetical example, an agent that can start a conversation about a multiplication question as a graphical interface on a desktop computer, then continue that conversation via text messages while the user is in transit, and then finish the conversation via a toy robot at the user's home. Intelligent represents the need of the agent to make reasonable and logical decisions about how it will assist its user. The agent needs a logical understanding of the pedagogical domain of knowledge that it is working within to tutor its user towards a better mastery. Personalized indicates that the agent can provide individualized assistance that is tailored to that particular user. For instance, if the agent detects that the user has a specific misunderstanding in elementary mathematics, carrying the 1 during addition, for example, then the agent can then dispense assistance that is related to that specific misunderstanding. Persistent indicates the agent's ability to continuously assist a user over longer periods of time and across incremental pedagogical subject matters. After all, an agent that can continuously offer personalized assistance throughout multiple school years will naturally have a more thorough understanding of a student's mastery over the subject matter than an agent that resets its knowledge every year. Lastly, agents for education denotes the continuing commitment of those engineering set assistants to keep in mind the myriad real-world and practical concerns that come with working in education, such as privacy, security, opportunity distribution, and many, many more. The overarching architecture of the TIP8 agent we have invented and are gradually implementing part by part is shown here. We refer to this architecture as the master method. It begins with the generation of a given test, T, using /consistent with Common Core standards at the relevant grade level, and also using the particular grade level axiom system phi sub k selected from reverse mathematics content. Part of the master method, and indeed a key part thereof, is the G3 solver algorithm. This is because generation of test T as a series of questions, Q sub I, are verified as correct and measured for difficulty by ensuring that A, the G3 solver can find a proof, denoted as pi, of the answer / key, denoted as alpha, and that B, a minimal proof is of the appropriate length, where minimal proof length gives us a way to gauge the difficulty of a given question. Further details of this way are unfortunately out of scope for this presentation. Here is a demonstration of G3 solver in its position as a key sub-algorithm for the master method. This sub-algorithm and the pseudocode provided therein should, for the most part, be self-explanatory. We're pleased to report that a run of an implementation of the G3 solver, in which calls are made to the aforementioned shadow prover system, returns a proof of the answer / key alpha in just 1.1 seconds. Now, some inevitable objections to this work have been anticipated, and we would offer rebuttals to them here. The first can be succinctly stated as, your approach falls prey to teaching to the test. This is an objection that educators are quite familiar with. In our case, we anticipate hearing it expressed quite loudly, since, after all, we are undeniably seeing to have AI teach by issuing and assessing performance on tests. However, the objection does not apply to our work, at least in our opinion, for a very straightforward reason. The reason is that in the case of math, at least at this early level, and the questions composing the test in question, the content on the test and what is to be learned is one and the same. This is especially true because many of the test questions present scenarios that match problems seen in quote-unquote real life. Even in the case of the simple math questions shown earlier, this is true. In fact, in trying to obtain the square footage of rooms in a domicile, but where information is not complete, it's quite possible that the figure and problem shown in a third grade question could be a real life one. The second objection, stated succinctly, would be, a major driver of the disparity you rightly bemoan is technology. The objection, fleshed out a bit more, would be, the economically disadvantaged suffer from a lack of access to computational technology. Examples being decent computers, adequate internet access / speeds, etc., etc. Your solution, since it requires students to be helped by your AI to have access to sophisticated computational technology, is a non-starter without these problems being solved first. In quick reply, we concede that AI-based remediation for disparity in mathematical prowess among American youth requires parallel thrust of effort to improve access to the technology necessary to enable the artificial agents that we seek. However, the fact of the matter is that even before the advent of calculators, Paper planes, pens and pencils, and slide rules were things beyond the reach of many disadvantaged students. And yet, certainly no one at the time could rationally maintain that pedagogical innovation presupposing the availability of such things should not be pursued. Things should be no different for us. Eventually, the penetration of computational technology will advance, and getting busy now on the AI enabled by that technology is simply prudent and planful. At the end of the day, AI-based education will always require computation, and computation will always require hardware and software of some sort. Fortunately, there are some countervailing factors in our favor. For instance, given the deployment of artificial agents of the sort that we are aiming at, disadvantaged students will be able to sharpen their math skills even if other shortcomings aren't fully addressed, e.g., less competent teachers, unavailability of human tutors, etc., etc. In reference to related works, at present we are unaware of any related works by others aimed at building artificial pedagogical agents that are based on an axiomization of mathematics in order to enable such agents to teach mathematics. Indeed, surprisingly, the use of results produced by reverse mathematics seems to be entirely absent in the area of AI-based/AI-infused math education. Of course, the previous sentence refers only to element number 4 of our logicist AI approach as described earlier. This element is certainly crucial and prominent, as the overall architecture of our system shows. Nevertheless, this element, as the reader has seen, is but one aspect of a number of others that distinguish our attempt to address the math proficiency disparity between the wealthy and the poor in the US. This naturally prompts the question, what about work by others that relates to other aspects of our particular R&D methodology? Quite a bit could be said about related works in the part of AI that is logicist/logic-based, and as most readers will know, intelligent tutoring systems in AI are well related to our work. However, discussion of specifics will have to wait for a full paper that expands upon the present abstract. In conclusion, we have introduced the audience to a grave problem in US K-12 math education, and outlined our proposed AI-based solution to it. There is of course much work that remains to be carried out. Concretely, for grade 3 math questions of the New York State variety, we look forward to conducting between-group experiments with subjects in order to ascertain whether treatment, i.e. use of an embodiment of our overall architecture with which subjects interact as a supplement to their standard in-school education, results in improvement in performance on the annual math test administered by the New York State Education Department. At the theoretical level, next steps include pushing forward with prototypes based on more sophisticated instantiations of the master method. For example, instantiations at the level of elementary algebra, in which even the first simple equations given to students involve both universal and existential quantification in formal logic, and hence call for an understanding of such quantification in order to be proficient.